Hi, I'm Luke Kane. Welcome back to Algebra 1. Today we're going to talk about special cases in system of equations. Remember the last time we solved a system of equation, we found one solution, which was at the intersection of two lines. Today we're going to look at two special cases. The first special case is the case of when our system of equations is graphed as parallel lines. And the second special case is when the system of the equations, the 2x2 system of equations, is graphed and we discover they are collinear lines. So here's what we did last time. We did a problem. We plotted two lines. We found at the intersection we found the one point, the one x and y, that would satisfy both equations. In this case it was x equals 1, y equals 3. Satisfied both of these equations over here. And we actually confirmed that that was true by checking, by substituting them into the equation. We got two true equations. So we found the solution, we checked it, and it was only one solution. That's it. But suppose we have parallel lines. Parallel lines are a different beast. By definition, there is no intersection. There is no one point that's common to both lines. Since that's true, then there is no solution. There is no one point that will satisfy both lines. All right, let's look at that idea from a slightly different perspective. Here is the two equations in question. Now, if we ignore the constant, they're the same equation, right? Y equals 2x. So it's going to be the same. All right? But now we add the constant, and the difference between the two is plus 5 minus 3. That's plus 8. That means no matter what x I put in to this first equation, this equation here is going to be 8 less. Let me show you with some examples. Suppose I put in minus 3 of the first equation. Well, what do I get out? I get minus 1. Put the same number for x into the second equation, I get minus 9. The difference is 8. Put in minus 2 and minus 2, the difference is 8, and so on. The difference is 8, the difference is 8. No matter what I put in, the difference is going to be 8. So there is no one x value that I can put in that's going to get the same y value out. So since there is no solution to both equations, there's no way I can simultaneously solve both of these equations. There is no one point that's going to satisfy both equations. Then there's no solution to this system of equations. Well, how about the case for collinear lines? And here we'll use this as an example. This system of equation, it turns out, is going to produce collinear lines. What does that mean? So how about this system of equations? Well, equation number 1 is in slope-intercept form. Y equals mx plus b. So we can actually sketch a draft of the, we can sketch a draft, see if I can draw it straight. We can sketch a draft of what this is going to look like when we plot it. There's the x-axis and the y-axis. Alright, so this is going to be the point 0, 4, right, because 4, that's b, which is the y-intercept. And the slope is going to be a half, so that means for every 2 we go over, we're going to go up about 1. That give us our second point, and we connect the dots, and we're going to get something that looks like this. All right, because I mean, basically, if we have, we want to test this before we do any serious plotting as to whether or not these lines are parallel, and then there's no solution. Well, let's take this second equation and let's put it into slope-intercept form and plot it. See what happens. Slope-intercept form, because that'll make it easy to plot. So I got x minus 2y equals minus 8. ugly looking minus 8, minus 8. Alright, so the first thing I'm going to do is get rid of the x, or at least put it over on the other side by subtracting x from both sides. That goes away. I have minus 2y equals minus x minus 8. So now I divide both sides by minus 2. That goes away. So now on the left-hand side, I got it in slope-intercept form. Now I got to do a little bit of math here. This is a minus 1 over minus 2x over minus 8 over minus 2. Now I can simplify that. That's going to be y equals minus over minus is half. So that's a half. And minus 8 over minus 2, well that all, oops, I forgot my x. Minus 8 over minus 2, that's going to be a plus. 8 divided by 2 is 4. Uh-oh. This equation is the same as that equation. Uh-oh. So if I were to plot it, I mean basically it's the same line. So I would just end up with one line. Or, as you might have learned way back in geometry, these are collinear lines. They're one on top of the others. Actually, collinear used mostly to refer to points. Anyway, interesting thing about this, since both my lines end up on the same point, that's a solution, that's a solution, that's a solution, that's a solution, that's a solution. Every one of these points on the line is a solution, so they're going to be infinitely many solutions. Infinitely many solutions. Alright, so what did we learn about the following system of equations? We learned that when we plotted it, it was collinear. It basically ended up as one line. Since each point on that line can be a solution, there are infinitely many solutions. So what do we learn? Well, we learned the usual case, we end up with the intersection of two lines. And when we have the intersection of two lines, we get one point. That one point, the x and y coordinates, will satisfy both equations. So consequently, you have one solution and one solution only. We call that a unique solution. However, there are two special cases. If we end up with parallel lines, if our system of equation ends up with parallel lines by definition never intersect. So there are no points that will satisfy both equations. So consequently, there's no solution in the case of parallel lines. Collinear lines, well, in collinear lines, basically, we end up with one line. So consequently, since we have one line, there are infinitely many solutions. Any point on that line is going to be a solution. We can look at this graphically. Here's the usual case where we have two lines, they intersect, they form one solution, and one solution only. Here's the case where we end up with parallel lines. They don't intersect anywhere. Since they don't intersect, there's no solution. And the last case was we have two equations, but the two equations are of the same line. And since we only have one line in question we're dealing with, there are infinitely many solutions. Any point on that line is going to be a solution. Alright, next time we're going to talk about solving systems of equations by substitution. Till then, I'm Luke Kane. Bye for now.